Hey everyone, this is Derek, and this is going to be the first of 3 videos. It's going to kind of lead up to the second derivative test. In this one, we're going to look at figuring what concavity is and finding that over either a point or an interval for a function. So concavity, that involves a second derivative. So we saw in the last section, first derivative. If our first derivative was positive, that means our function was increasing. That's like these two. And if our first derivative right here was negative, that would be decreasing. That would be those two. And so for a linear function, right, it increased at a constant rate. So this is where the rate of increase or decrease is changing, and that's the second derivative. So right now, as I'm making this, we're all staying home for COVID. And so this one is sort of the flattening the curve that we're hearing a lot about. What we're trying to do is, here the rate is steeper. If I keep drawing tangent lines, it's not quite as steep, not quite as steep. So the rate of increase is decreasing at each interval until up here, hopefully eventually the rate of increase is 0. And then we end up with this behavior on the other side. But so that's the idea of concavity, is that it's how the rate of change is changing. So if we're talking about velocity, then this would be acceleration, would be the second derivative. So it's how you're speeding up or slowing down. So we can kind of look at these for concave, and we have kind of 2 flavors. We have concave down and we have concave up. And so I kind of have them broken out by the signs on the first derivative and then the signs on the second derivative, and then what those will get you. So if your second derivative is positive and your first derivative is positive, you'll have increasing and then concave up. And so concave up, here the slope is fairly flat, and you can see it's getting steeper and steeper and steeper as we move to the right. And so the rate of change is increasing along with the slope itself is increasing. So for concave up, concave down is like going to be things like parabolas opening down. That's basically what a concave down is going to look like. Up is going to look like a parabola opening up. So concave down, one thing they'll always say is the idea of it, does water run off of it or does it hold water? So concave down, if I poured water on that, the water would run off. Concave up, if I poured water, it would hold water. So that's sort of another way of thinking of those shapes and sort of which one is it. What we'll see in the section going forward is that the concavity can change. So that's not a very good looking polynomial, but pretend. So right here, this piece is concave down, but then something happens somewhere around here where you see here the water would be running off of it, but somewhere in here it starts to then hold water. And so we'll see in the second video, this is going to be what's called an inflection point. Okay, so this first one's pretty straightforward. So given the graph f of x, over which interval of x values is f prime of x greater than 0? So this is saying, where is the derivative positive, essentially? And remember, the derivative is the slope of the tangent line. So we can kind of think of this as, where is the slope positive? Like once we kind of get through all the language in that's really what we're looking for. And so you can see we got this parabola, and it's gonna, let me just kind of sketch in the axis of symmetry there. So all along this side, it's increasing. It's slowing down with its increasing, but it's still increasing until right there it'd be flat. So right there, our first derivative would be 0 because the tangent would be horizontal. And then you see after that, it's going to go negative. So which values is the slope positive? And these are x values. So that's going to be from negative infinity up to negative 2. We don't want to include it because, again, that's where it's 0. And which intervals of x values is f prime of x less than 0. So that means the slope in this case would be negative. And so that's the other side. So negative 2 to infinity. And then what is the concavity of the function over the interval negative infinity to infinity? So on its domain. So remember, if it doesn't hold water, if water would run off, that would be concave down. Okay, so coming back here to our definition page. So when the second derivative is positive on any given interval, and that means the original function is going to be concave up on that interval. And then when the second derivative is negative on an interval, it'll be concave down on that interval. And so it could be, and here's where it gets a little bit of a hard on the brain. Notice it can be decreasing concave down and increasing concave down. Likewise, it can be decreasing concave up and increasing concave up. So you can't associate the concavity with, is it increasing or decreasing, because it can do it on either version. It's more of like concave down. Again, water's going to run off it. Concave up, water would kind of puddle into it is the idea. And that could be, again, decreasing or increasing. But if our second derivative is positive, it's going to be concave up. Second derivative negative, concave down. So here, we're supposed to find the intervals where the function is concave up or down, enter d/e if it's not concave upwards or downwards. So what we'll do is we'll get to the second derivative and then figure out what the sign is of it where. So taking the first derivative, so we'll go 2 times 4 for 8, x now be to the first plus 3. And then one more, we'll go to the second derivative. And that's just going to be 1 times 8 is 8. And so f double prime of x is 8. 8's a positive number. So that means f double prime is greater than 0. And so remember, when we have this, it's going to be concave up. And then f double prime is 8 everywhere, right? So it's always going to be 8. It's always going to be positive. So it'll be concave up on the interval negative infinity to infinity, because the sign never changes. It's always 8. So then concave down, well, the whole thing is concave up, so that's where we'd have a d/e, is that it's never concave down. Okay, same directions as the last one. This one we'll just have to pull out maybe the power rule, the chain rule version power rule. So we'll do f prime of x. Remember, we do the 3 times the invisible 1, so that'll be 3, and then 2 minus x. And then 3 minus 1 leaves a 2 up there. And then we multiply that by the derivative of the inside. So remember, we kind of take the derivative of the outside, we leave the inside alone, and then multiply it by the derivative of the inside. So the derivative of the inside is just going to be negative 1. So I'll just throw a negative right there on that 3. And then that's our f prime. F double prime, we'll go 2 times negative 3 makes negative 6, 2 minus x, and we'll take 1 off of there. So now that's like to the first, and that will be times, again, that same negative 1. And so that will be negative 1 times negative 6 is like 6 times 2 minus x. So that's our second derivative. And then the same as when we did the first derivative test, if I look and see where this x is 0, then that's going to tell me where the signs are going to have, where there can be a sign change. Because if I find the 0, and this is a linear function, it's going to be positive on one side, negative on the other. So for this, if I set 2 minus x equals 0, bring my x over, 2 equals x. So we would go like that, and we'll put 2 in the middle. And then we'll just do a couple of test points like we do. So we'll put in a 1 and a 3 would probably make sense. And this is, we're testing f double prime, because that's what we want to see, where is it positive and negative. So this is a number line of f double prime of x. So if I put a 1 in here, 2 minus 1 would be 1 times 6, so that's positive. And there's our 0. And if I put a 3 in there, 2 minus 3 would be negative 1, so that'd be negative 6 for negative. And so this one we would say it's going to be concave up, where it's positive, so that's going to be from negative infinity up through 2, and then concave down on the other side where it's negative. So from 2 to infinity. And then notice I am not including that 2, right? Because that's where it's 0. So that's actually going to be what the next video is about, which is called inflection points.